ways buildings are designed and in the way they are built. Sorry, that's funny. There's a slide missing. But anyways, okay. Okay, sorry. Anyways, so when it comes to building design, we obviously need to improve building performance. Given climate change, we need to reduce the energy that is consumed in buildings. And this is really a factor or a product of the design of the building fabric, the way occupants behave in buildings, and of course, climate itself. When it comes to the construction process, this is something that has been addressed a bit less. It will also be increasingly affected by climate change. And we need to take into account in a warming world heat stress and the way it affects workers on construction sites and how that can influence project economics. So I'll start with discussing building design and how energy demand in buildings is a function of the building fabric, the way buildings are used, and the climate. There is a well-known gap between the planned performance of buildings in terms of the energy that is expected to be consumed in them and the actual performance once they're occupied. Usually, that performance is less good than was planned. And the main reason for this is that we are not very good at predicting how occupants will behave in buildings, how they will use the building systems, when they will actually be inside the buildings, and what the buildings will be used for. So we need better ways to analyze user needs and translate them into project requirements. Well, this is actually a very well-known process. It's called building programming, project briefing. But it's not very well integrated with sustainable building design. So we have very sophisticated tools for simulating building energy consumption, for optimizing building fabric design. But if we base that on the wrong assumptions, then the outputs of those tools won't be very useful for us. So I'd like to demonstrate that with a study we carried out on 3 residential buildings in the city of Eilat in Israel. That's located at the very southern tip of Israel. It's a very hot and arid desert climate. And you need a lot of energy in order to cool the buildings, especially during the hot seasons. Now, these 3 buildings are different in their design, as you can see. They were also, although they were all residential buildings, so belonging to the same category, they were also very different in terms of their occupants. One building housed families, the other housed hotel employees, and the third housed students. A basic thing is, when are the occupants expected to be inside a building? That is one of the things that probably determines most how much energy will be consumed. And as you can see, these different groups occupy or are present in the buildings at very different times. The families are using their apartments mostly in the evening and in the morning, the nights, of course. The presence of hotel employees changed throughout the day according to their work shifts. And the students were actually present more than any other group because they were studying in their apartments, presumably. Now, when we checked the actual energy consumption in these buildings, they were quite different. But of course, the design was also different. So it's a bit difficult to tell what is a factor of the occupancy schedules, what is a factor of the building design. To analyze this, we used building simulations to virtually shift or change or substitute these groups to test what would happen if one group occupied the building or another. And then we saw that there were certain trends. The absolute differences when we changed the occupants in each building were quite striking. And this also relates to the way these buildings should be designed. For example, we tested what happens when you rotate the building. So when the long facade with many openings faces the south side, it's obviously exposed to the sun during midday, heating up the building, require much more energy to cool it. But you only need that if there are people present in the building during the midday. So again, how much energy is actually consumed is both a factor of the orientation of the building and of the user behavior, or building occupancy in this case. The same is true when you rotate it to face east and west, then those facades are exposed in the morning and in the evening, and more energy is consumed if the occupants are present at that time in the building. Well, we looked at what happens when you increase the insulation of the building facade. Of course, each additional centimeter of insulation will reduce energy consumption, but with diminishing marginal returns. You get less and less reduction with each additional centimeter. But again, this depends on who the occupant is. If they consume much more energy, then it might be more worthwhile to add additional insulation than if they use less of it. And in this case, this was just a function of when they're present in the building. So it's not much more sophisticated than that. Now, it's important to remember that when buildings are actually designed, even when we use sophisticated simulation and optimization engines, we base these on certain assumptions, which are usually very generic occupancy schedules defined in standards. But these are often wrong. So when we compared the actual results with what would happen if we had used those generic schedules, we saw that there are very large differences in the amount of energy consumed, the actual energy consumed, versus what would be expected if we had based ourselves on the generic assumptions up to 23%. So that is a way to show that the optimum is really a matter of context. It's not generic. And we should be very careful when we design buildings to base it on a deep analysis of user behavior and user needs that we can translate into project requirements. But of course, clients demand not only well-performing buildings, they also want it to be delivered on time and within the planned budget. And this usually does not happen. So we have not only problems with actual performance versus planned performance, we also have problems with the actual delivery versus planned delivery. Most projects are over budget, behind schedule, and so forth. So in another project, we designed and constructed 4 different net zero energy communities or settlements. And we had quite ambitious targets regarding their performance. We wanted the energy consumption to be very low, on-site energy generation from renewables to be very high. But we also wanted these projects to be less expensive than is usual, so that they are affordable. Because after all, those who will need such project most are the occupants who suffer from energy poverty. They're the ones we need to help with saving on energy bills. But a net zero energy building or community requires quite sophisticated technologies. And once you start using those, the odds of having cost escalations, of overrunning your budget, increase, because it's quite complex, right, to design and to actually apply these technologies in a building, in a community. So we had to very carefully plan the whole delivery process, from selecting the technologies, to sizing them, to certifying, to planning supply logistics, to installing them on site, and to carefully test them before the building is occupied, and of course monitor those buildings after they were occupied. So we planned very carefully how exactly all the different components would be installed on site. Here on the left side, you can see how we planned the installation of an advanced HVAC system, step by step. And on the right side, you can see the installation of a wind turbine, showing the exact steps and what equipment would be required. This was important to us to avoid these problems that occur on site, which are very costly to repair once they have occurred. So we wanted to prevent them beforehand. And of course, we also had to take into account the interfaces between the different technologies. Now you notice there are very few people in these images, also in these, and that was on purpose. We wanted to use as much as possible autonomous systems. And this is also related to coping with climate change, as I'll explain in a minute. So we wanted to plan what would happen on-site, but also what would happen off-site, because after all, we don't build buildings out of raw materials. We assemble them out of components that are manufactured off-site. So we wanted to make sure that what happens off-site is also done efficiently, to plan the assembly in the factory in as simple a way as possible, carefully standardizing the interfaces. Interfaces are in general very important because that's where usually the problems occur. We also wanted to plan the assembly lines to make them as efficient and reliable as possible. So those were all attempts to prevent beforehand problems that would arise and cause delays and cost escalations. Of course, the quality of construction is also very important. I said that buildings underperform because we don't anticipate the user behavior correctly, but often there are also problems with the quality of construction. So we also needed to make sure through detailed commissioning processes that we would check all the systems, all the technology, including the building fabric, to ensure that they perform as expected. For example, we could use thermal cameras and machine learning to identify thermal bridges in the building fabric. Now, I was always interested in how we can enable better construction of better performing buildings and how we can use technologies for that. But lately I'd started to think of how this might change given the global warming effect. Because after all, global warming is mostly about additional heat. And this heat affects most people who do physical work outside and are exposed to this heat. And this is a major problem. It is already now a problem, but will just become worse. So those construction laborers who work on site, they are of course exposed and affected much more by heat waves like the ones you've experienced here in Britain than other people. And once they're affected by heat stress, their productivity goes down. And once their productivity goes down, delays occur, and eventually this will affect the profitability of the contractor. I might say, hey, why are you talking about the profitability of the contractor rather than the health of the workers? Well, because in practice, that is what right now drives decisions regarding how we build buildings. That's the truth, that's the reality. So that's what we wanted to test to begin with. I was interested in understanding when would we cross a certain critical threshold? When would the actual heat stress create such impacts on productivity that delays would occur that actually would make the project unprofitable for a contractor under current conditions? That was the question I asked myself. And to test this, we took a reference project, a conventional 30-story residential building made with cast-in-place reinforced concrete. And we simulated what would happen if we built this project in different locations in Israel, under different climate change scenarios, and of course, throughout the coming century. In order to understand when would they cease to become profitable for a contractor on current conditions, and what we found was there was more or less 7% of the project duration that would be delayed, that would cause the project to cease to be profitable because of additional labor costs and indirect costs and so forth. So when would we have these 7% of delays? That was the question. And what we found was that on average in Israel, this would occur in about 20 years. Okay? So in about 20 years, we would be facing reality where we could not continue to build buildings as we do right now because of the additional heat stress that negatively affects the productivity of workers. But this is only on average, which isn't very informative because even though it's a small country, you have different climate zones, in the country. So we wanted to test, okay, what happens in each location? When would we reach this critical threshold in each location? So first we have a lot, you remember, from the 3 residential buildings, and we see that we are already there in a lot, because as I said, it's a very, very severely hot climate, which is of course interesting. So what's happening there right now? Well, construction is much more costly in a lot. Workers only work during the mornings and late in the afternoon in the hot season. But there are other factors that increase costs there. It's very isolated, so transportation costs are expensive, so it costs a lot to bring in materials and components to the site. So it's not really clear that this is just because of the heat. But when we look at other locations, we see that we reach this critical threshold in about 15 years, 20 years. In Jerusalem, we don't reach it at all. So it really differs. You see these locations are really close to each other. It's a very small country, but it really depends on where you are. Now, why am I interested in this? I mean, you could say, well, when it happens, the contractor will notice and he will just change the way he works. Not necessarily, because it is actually quite difficult to understand why delays occur in a particular project. You might think it's obvious, but there are so many factors affecting the progress in a construction project. Progress monitoring isn't very effective, and understanding the causes for delays is even more complex. Right now, they basically try to identify legal causes to make claims so that the client pays them more. That's not the real cost. It's probably some kind of an excuse very often. So we don't have very good information on this, and it would probably take a very long time until contractors realize that these delays are due to climate change. On the other hand, in order to change this reality where we rely on manual labor by people on a construction site, in order to change the way we build, we need to reorganize the entire industry. And that would take time as well. So what I think will happen is that there will be a large overlap. We will realize that it happens very late, and then it will take us a very long time to change the way we build. That was why we thought it might be interesting to identify beforehand, proactively, these expected thresholds, to give industry a time to prepare. Of course, the delays are concentrated in a specific season, so 90% of them are during 5 months of the year, but alternatively, we would only build during part of the year, and I don't think that's a very good solution to this problem. But so far, I've just talked about the contractors, not about the workers themselves, who would suffer, of course. Their health would deteriorate from working so much under such strenuous circumstances or conditions. And I expect that at some point, this will be regulated. People will start to say we cannot allow contractors to continue to employ workers under such conditions. In fact, when we look at some countries, for example, Qatar, which right now has a climate similar to what we can expect in a few decades, there is already such regulation in place. So they have rules for when workers need to stop working or when they need to take a rest based on meteorological data. And when we simulated what would happen if we applied such a regulation, of course, the critical threshold is much sooner. Okay, so depending on the regulation that will be implemented, contractors will face this problem much, much sooner. Not in 20 years, but probably in 10. So that's very soon. So what do we do? Well, there are a number of things we can do, and we should. So again, I'm going back to this project where we said, we can move some of the work off-site so that it is executed under controlled conditions in factories. And in fact, we can use in factories autonomous systems, robots much more effectively and easily than on a construction site because we have a production line that's repetitive. But also when we work on-site, we can very carefully plan the assembly and installation processes so that we rely less and less on human effort, more and more on use of equipment. And that is something that can help us reduce the exposure of workers to this heat. It is also something that can improve the quality of the construction, that it can improve the performance of the building. So we have actually these two gains at the same time. We get better performing buildings, and we also improve the delivery process so that it is less exposed to the effects of climate change. Well, this is a nice story and these are nice pictures, but is this actually possible? If I need to do it in 10 years, can I do it in such a time? Well, I think so. And I'm sorry for those who were yesterday at the debate. I'm going to go back to some of my points there. But as I said, we're in the midst of a construction robotics revolution. And I think this is an interesting story. Do I have a bit more time, a few more minutes? Yeah, okay. So let me tell you what happened. So in 2018, a Chinese real estate company called Country Garden decided to set up a construction robotics company. You may have heard of Country Garden, but got into a lot of financial distress later on. But then this wasn't the situation, and they were having problems recruiting workers because, after all, who wants to work under such conditions? They're just getting worse. It's just getting hotter and less pleasant to work on a construction site, and fewer people want to do it, especially if living standards are rising, fertility rates are dropping, there's a lot of employment for young people. They prefer not to work on a construction site at all. So Country Garden was facing this problem. They could actually not execute their projects according to the schedule because they didn't have enough manpower. There was a labor shortage. So they set up this company, and they did it the way, apparently, things are done in China. They took 3,000 engineers, and they told them to start developing robots for every task on a construction site. Okay? And they developed dozens of robots. And of course, it was a trial and error process. To begin with, they failed completely. Then they failed a bit less. Finally, they had robots that worked. Similar to what happened with electrical vehicles, with PV panels, they tried and tried until they reached a very high performance level. Then Country Garden got into trouble. They closed down their robotics company, Bright Dream Robotics it was called. But all those engineers who had worked at that company, they went out and set up their own companies. And you now have many, many companies that are developing many different kinds of robots. And they do all kinds of things. They can do wall plastering and wall painting and floor tiling and window installation and rebar tying. Almost any kind of task you would think of. And they're commercial products. We can actually buy them and start using them on a construction site. And that's actually what is happening right now. So that is very exciting. And it's not just Chinese robots. They're the focus of all this activity right now, but you have other companies elsewhere in the Netherlands and in Israel and North America. So this is where we're going now. And that is actually really good news because, of course, using such a robot on a construction site under very hot conditions is much less of a problem. So if we combine that with off-site manufacturing and assembly, we can reach a stage where we have efficient construction processes, building high-quality, high-performing buildings without exposing workers to heat stress, which is unhealthy for them and detrimental for the progress in the project. So I think we see here three forces that are now converging to require the construction industry to reinvent itself, primarily because of climate change at the moment. On the one hand, we need to improve the performance of buildings. And as I said, this requires a number of things. It requires us to better understand user needs, user behavior, translate that into project requirements to base our building design on correct assumptions, And that way, we'll eventually get buildings whose performance matches the plant performance when we carried out those building energy simulations. We also need to improve the quality of the construction. Of course, we need to ensure that with commissioning processes. But at the same time, we need to change the way we build, because we can simply not continue to employ workers on construction sites under such impossible conditions. And it'll become worse, and we're sorry for the bad news, but these heat spells you just had now are not an aberration or an anomaly. They're just a new trend. And this happens in Northern Europe. You can imagine what happens in the Mediterranean, in India, and other hot countries. So we need to change the way we build in order to expose laborers less to heat. But we also have an opportunity here. Because of automation, because of the autonomous systems that we can now use off-site and on-site, that are actually mature enough. I was very skeptical of construction robotics for a very long time until I saw that it actually works, and it does. So I think this is really good news. And that way we can, adjust both the way we design buildings and the way we construct them. So yeah, that's it for my presentation. I'll be really happy to hear your opinion on this, maybe have a discussion, since we have a little bit of time left, I think, right?
Thank you so much.